Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey, Houston, we don't have a problem. Today we're going to talk about electrical power. Now, we have learned quite a bit about power in our course. We've learned that power is energy used up in time. We often use cycling examples. If you have somebody who is more massive moving at the same speed, they're going to have more power than somebody else in the same amount of time. Or I weigh a certain amount, and if I'm working with somebody who weighs less, then I'm going to have to exert more power if I'm going to move at the same speed. A lot of things with power we've talked about from a kinematics perspective, but when we talk about electricity, power is still power. So let's do a quick review of what power is. Power, by definition, is energy divided by time. All right, so work divided by time, energy, some form of energy divided by time. And we've learned about electrical energy that follows Coulomb's law. All right, so and note the units on this will be joules per second. So it's kind of how fast you use up energy. But when we talk about electricity, there's lots of equations that power equals. You can rearrange the equations. I'm going to get into all the details, but P can also be equal to I times V. These are like the critical key equations, I being current, V being the voltage. Also, P equals, there's ways to kind of rearrange all these equations. I squared R, the current squared times the resistance, the number of ohms in a circuit. And then P, lastly, is equal to V squared over R. So these three equations, actually technically these four equations, help you to solve a lot of problems when you're doing these things. So let's cut to a video clip with a guy who's going to do a quick experiment. Let's watch for a second. So we've got two kinds of wire, nichrome and copper, one 2.7 ohms and 1.1 ohms, and he's going to pass a huge amount of electricity through both the same exact current. Now what he's going to do, he's going to plug it in, and what do you think is going to happen? Notice how the nichrome wire is just burning to the core because it had low or high resistance, and the high resistance made it get hot. So probably what you expected. So power, again, our equation that we had up a minute ago, if it has a higher resistance, P equals I squared R. If the R gets higher, then you're going to have greater power because you're putting the same amount of current through both wires. And so the resistance up, the power goes up, it catches on fire. I've also got this equation sheet that explains kind of all of the electricity equations. And the power ones are right here kind of in the middle. You can see them there. By the way, if you're watching this just on YouTube, I'll put a link to this equation sheet. It just helps you, I think, if you've kind of got a list of every kind of electricity equation that's applicable in a physics class. Hopefully that helps you. So let's finish off with an example problem. And here's the example problem. We have a 1500 watt heater, and it's plugged into a 120 volt outlet. What current? So we've got three parts, part A and a part B and a part C. In part A, we have, it says, what is the resistance? So if you remember back, page to our equation sheet, the equation I'm going to use for this first one is just P equals IV. And we know the power was 1500 watts. So I'll just say 1500 watts is equal to I times the voltage, and the voltage was 120 volts. I do some math, some simple algebra, and I get 12.5 amps. So pretty easy. Question A, it's just plug in a jug, right? Letter B, a little trickier. Letter B is asking for what is the resistance. So we're going to pull back from one of our equations. Look at the equation sheet if you don't. And I can use the equation P equals V squared over R. Well, the pressure is still 1500 is equal to R is 120. So 120 squared over R. I do algebraic manipulation, and I get R is equal to 9.6 ohms. And then the last question, part C, is really the hardest question. I love this question, though. It says, how long, very, very applicable question, if this is your heater at your house, and it's 120 volt outlets, how long is it going to take to heat up this room that's 3 by 5 by 8 meters 10 degrees Celsius. So it's a cold day. You want to raise it up 10 degrees. What's it going to take you in terms of energy? Or time, pardon me. Now time, wait a second, time. How am I going to do time? Well, time, the only equation with time in it is the actual kind of power equation. Power is energy divided by time. So if I can find the energy, I know the power. The power is 1,500 watts. So it's 1,500, it's going to go right here, and I need to find the energy. Now, thermal energy, if you recall, and if you don't know, here it is the equation Q equals mc delta T. Now, let me talk about this. Q is heat energy. A little q is charge, measured in coulombs. This is measured in joules, okay? So if we knew the mass of the air times the specific heat of the air, the change in temperature. Notice we've got the change in temperature. You want to raise it 10 degrees. We know that the specific heat of air is this 1006 number. And so I have to find the mass of the air. So the mass of the air is a little tricky. And so the first of all thing, I've got a room, right, that is 9 by, what is it? 3 by 5 by 8. So when I take 3 times 5 times 8, I get 120 meters cubed. That's the square or cubic volume of the room. Now I need to convert that to grams, and they gave me a conversion of the number of, what did they give me? They gave me the density of air. It says that 1 meter cubed has a mass of 1.20 kilograms. And if you set this up dimensionally, you'll discover that the meters cubed cancels. So my mass of air is 1.45 times 10 to the 6th kilograms. Then that number goes in here. So Q is equal to 1.45 times 10 to the 6 kilograms times my specific heat of the air, this 1006 number, 1006, there's units, I'm going to be lazy, and then 10 degrees. When we multiply this out, pardon me, this is 144 kilograms. So this number is 144. Then when you multiply this, you get 1.45 times 10 to the 6 kilograms. Or not kilograms, I had it wrong. This will be joules. Well, guess what? That's equal to your E that you're going to plug into here. So now what I'll do is I'll say on the P, I'll say my power was 1,500 is equal to 1.45 times 10 to the 6 joules divided by time. Algebraic manipulation, I get time. You'll divide this by 1,500, really, won't you? Yeah. I get 966 seconds. And that's not a very useful unit. In this case, when you have that many seconds, there's 60 seconds in 1 minute. I divide, and I can get the number of minutes, and I get 16.1 minutes. So it takes 16 minutes to heat up that room, 10 degrees Celsius. So Houston, power really is about these equations. So the equation sheet that we have here, you want to use this equation sheet over and over and over again, because it really depends on if they're asking for the current, they're asking the voltage, they're asking for the resistance, or you may have to utilize some function of the energy equation to solve the problem. So Houston, we don't have a problem. We'll see you in class.